Okay, Year 10, welcome back to your next living room lessons. We are continuing our look at climate change. Hopefully you all got on all right with last lesson. I know it was a bit longer, but as I say, loads and loads of really interesting stuff, I think, anyway. So last lesson we were obviously having a look at the causes of climate change, and today we're going to come to have a look at something a little bit different. We're going to have a look at the evidence. So what evidence do we have for the fact that climate change is happening? So what you will need is your exercise book, a pen and ruler, your phone, and the carbon cycle sheet. And this is one which, if you can print it, you're going to make your lives 1,000 times easier. Otherwise, it's quite a complicated diagram to copy out. So if you are able to print it, I would really recommend that. Okay, so we will get started as usual with our jog your memory. So 3 quick questions. What is the definition of a glacial time period? Give 2 examples of high pressure weather hazards, and give a social issue for London as a global city. So pause your phones, scan the QR code, big juicy, stay home today, and have a go at this for me. Hopefully you've had a go at that. As I said, today we are coming on to have a think about the evidence. So we're going to be looking at the different evidence that suggests climate change is happening. And we're mainly going to be having a look at the evidence that there is more carbon dioxide, because last lesson we focused on the fact temperatures are increasing, and we touched on carbon dioxide at the end. And what we're going to be thinking about today is how we know there is more carbon in the atmosphere and the link that has to temperature. Okay, so titles in your book today are evidence of climate change. Please write that out and underline it for me. So we're going to start off with 3 key terms here. So we've got carbon cycle, carbon sinks, and carbon sources. So a carbon cycle is the flow of carbon between various stores. So it's the flow of carbon constantly occurring within our planet, because carbon it's always been here. It makes about 1% of all of the gases in the earth, but the actual physical carbon has always been in our planet. We have got carbon in us. There is carbon in the atmosphere, carbon in the oceans. So the carbon cycle is looking at the movements and flows of that carbon. Carbon sinks or carbon stores are places where carbon is stored over a very long period of time. So it's places where carbon is held. So at the bottom here, I've got 3 images of different places carbon is. So carbon stores are. So when you write out this key term, I want you in your EG to list these 3 for me, okay? And then carbon sources are places where more carbon is emitted than it is absorbed. So carbon sources are places that are producing more carbon than they are able to take in, okay? So what I'd like to do first of all is pause your video, copy out these 3 terms, and as I said, after the EG, please can you write our 3 different sources and stores here for me. They should be quite straightforward. Okay, so just to check that you've got these, so our 3 are, so it would be places where carbon is stored over a very long period of time, e.g. trees, soil, and the ocean. These are 3 of our largest carbon sinks, carbon stores on our planet, okay? So we're going to have a look at the carbon cycle, which was one of those key terms you just looked at, which, as I said, talks about the movement of carbon around the planet. So the first thing I want you to do before you have a look at this diagram is scan the QR code or copy out the link and watch this video. It's a prehistoric bite-sized video, but it does explain really nicely the impact of carbon moving around our planet, okay? So what I'd like to do is scan the QR code, watch that video, and then have a look at this carbon cycle here. So this is a snapshot of where carbon is held. And what I'd like to do first of all are name a place where there is a very fast transfer of carbon, and name a place where there's a very slow transfer. So here is a little key which shows you the different colour arrows show you the speed of which that carbon is moving within our planet, okay? So all I'd like to do is watch this and write fast transfer equals slow transfer equals, all right? Okay, so our fast transfers that you could have put down were burning fossil fuels, fires, photosynthesis, and respiration. These are all really quick. These happen in less than a year. These are quick flows of carbon. They happen very, very quickly. Whereas our very, very slow ones, there's only one that's very, very slow, which is the slow between sediments. Okay, so sediments in the ocean. But we also have slightly slower ones. So we have composition, decomposition, sorry, so the decomposition of the soil, so the soil rotting away, that is a slow transfer of carbon. And then we have the transfer of carbon within the ocean. So this is also a very slow one. As it moves from kind of high ocean to deep ocean. So these are slow transfers of carbon. So what I'd like to do next, you should all have the carbon cycle sheet in front of you, which has this diagram, but slightly different. And what you will see next to each of the different transfers, there is a box, but that box has not got anything in it. Underneath, you've then got this table, which have got our 12 different transfers of carbon on this carbon cycle. So what I would like you to do first of all is on your sheet, go through and number the different transfers. So I will do the first one for you. So fossil fuels such as coal, gas and oil store carbon for a very long period of time. So here are our fossil fuels underground storing it. It's not them being burned, so you wouldn't put it here, so we would put our number 1 here. Once you have put all of your numbers in, the next thing I would like you to do is on your key, colour code your carbon stores as one colour and your flows, so movement of carbon, as a different colour, and then highlight each box, each number, as to whether that is a store of carbon or as to whether that is a flow of carbon. Okay? So pause your screens. This is complicated stuff. This used to be A-level. I didn't do this in GCSE. But pause your screens and have a go at this for me. Let's talk through this. So one thing I've added in here is my key. So my carbon stores are in yellow and my flows are in orange. So as I said, number 1 is down here. These are our fossil fuels such as coal, gas and oil, which are stored for a really long time. We know it takes millions of years for these fossil fuels to be created. So these are stores which take a huge amount of time. So number 2 is the fossil fuels then being burned. And as we saw, this was a quick transfer. So it takes a long time to produce this carbon, to store it, and then it's transferred really quickly when we then burn those fossil fuels. Number 3 are the plants taking in carbon, so it's the downward arrow, and this again is a flow because they are taking in that carbon during photosynthesis. Number 4, trees store carbon for hundreds of years. So within trees, there are huge amounts of carbon held in the roots, in the bark, in the twigs, in the leaves, okay? So this is a store of carbon. Number 5, decomposition of leaves, branches, return carbon to the soil. So as these leaves are, the trees rot, they fall down, they decompose, and it puts carbon back into the soil, and this is another flow. Living things breathe out CO2, respiration. So this is 6, so the trees are then releasing more carbon as well. So not only do they absorb it through carbon dioxide, but trees, humans, animals, all living things, through respiration, through breathing, breathe out carbon dioxide. The burning of trees also releases CO2, so this, as we saw, was a very quick transfer of CO2. Number 8, CO2 is dissolved in the ocean, so it dissolves into our seas. Number 9, there is CO2 in the atmosphere, so we have it in the sky in gas form. Number 10 is when CO2 moves between the ocean and the atmosphere. So as the ocean is evaporated, CO2 moves back into the atmosphere. Dead plant matter is compressed and turns into rock. So as our rotting soils then get compressed and forced downwards, they turn back into rock, and those rocks store huge amounts of carbon. And this is what we call liquefaction. And our last one, number 12, dead algae and seashells contain carbon. So shells are hugely made up of carbon. Dead animals rotting at the bottom of the ocean release carbon back into a store which is held at the bottom of the ocean. So as we can see, there are a range of stores and a range of different flows. In the last diagram you were looking at how fast they were. This is showing you how you find them on the carbon cycle. Now, as I say, this is complicated stuff. I'm not expecting you all to have understood this first time around, but you should now hopefully have a diagram that looks a bit like this. Okay, so we're going to have a look at a graph that looks terribly complicated, but before we do, I've got another quick key term here for you that I want you to get into your books. And this key term is a carbon flux. So a carbon flux is the amount of carbon that moves between different carbon sources. So the movement of carbon between the ocean and atmosphere. So a flux is that release, that movement of carbon. And as you can see on this graph, so what this graph is showing you is 0 is a positive flux, so when there's more carbon being released, and then Below zero, these are our negatives. These are carbon being put back into storage. So as we can see from this, from 1880, our carbon flux was fairly low. There wasn't a huge amount being put back, there wasn't a huge amount of emissions, there wasn't a huge amount being stored again, but it was fairly equal, all right? And then as we reached kind of 1940s, 1950s, this flux increased hugely. Partly, as we can see, due to fossil fuels and cement. They are one of the biggest contributors of this carbon emission, this positive carbon flux. But the negative carbon flux is also quite high. We can see that carbon is being put back into a lot of the stores. So what I'd like you to do is have a look at this graph. I know it's complicated, but hopefully I've just explained it a bit for you. And I just want you to copy out these two sentences describing carbon fluxes. Okay, so pause your screens and have a go at these sentences. Let's go through these then. So carbon emissions such as land use change and fossil fuels are increasing. In 2000, fossil fuels and cement reached 38 CO2 flux. So the amount of carbon emissions, the positive carbon fluxes are increasing, especially fossil fuels. There were a tiny amount at the beginning, now it's a huge amount, okay? Carbon sinks such as land, atmosphere and oceans are decreasing. So the amount of carbon held in sinks is reducing. In 2000, oceans had decreased by -40. So whilst the amount of carbon being produced and being emitted is increasing, the amount being stored is decreasing. We're extracting huge amounts of carbon, which means that there are much less in sinks than there are in kind of the atmosphere and fossil fuels and in land use. So we can see that over the last 120 years, the carbon fluxes have increased and we are producing and moving carbon at a much quicker rate than would naturally happen. Okay, so the next thing I want you to do is have a look at this example. So this is a more stripped back version of carbon, the carbon cycle, and this is the carbon cycle within a tree and the impact of cutting down trees is having on the carbon cycle. So what I want you to do next is pause your phones, pause your videos, have a look at this diagram, and I want you to answer these 4 questions. So question 1, name an input into a carbon cycle. So what is an input? How does carbon get into the cycle? What is the process? One of the processes you can pick out from here which introduces carbon to the carbon cycle. And then what is an output? What is a way that the carbon leaves this carbon cycle within a tree? How is carbon lost from the tree? Then give 2 reasons why the burning of tropical rainforests will increase the amount of carbon dioxide in the atmosphere. So there's the obvious one that we get from releasing it, but I want you to think about what could be a second reason why tropical rainforest destruction is bad for carbon. And why is it important to create more carbon sinks? What could we create? Okay, so answer these 4 sentences in full sentences. So an input of the carbon cycle is, an output of the carbon cycle is, a reason it is bad to cut down the rainforest is. All right, so full sentences, so this makes sense when you are revising it and filling in your revision packs. All right, so let's go through these. So an input would be the solar energy. The solar energy inputs carbon into the carbon cycle. Photosynthesis puts carbon cycle in. An output would be respiration. So as the trees breathe, they respire carbon back into the atmosphere. 2 reasons why burning the tropical rainforest will increase the amount of carbon dioxide. The first one is through burning the trees, because through burning it, you are quickly, we know it's a fast release, it's quickly releasing carbon back into the rainforests, back into the atmosphere. We are also reducing the amount of photosynthesis, so there are going to be less trees to take carbon from the atmosphere. And we also, trees stop the rainwater, which has huge amounts of dissolved carbon in them. So there's going to be more rainwater running straight over the Earth's surface that then goes back into rivers, which means it's going to end up back in the sea. So I've given you 3 reasons there, okay? So why is it important to create more carbon sinks? Because we need to balance the sinks with the fluxes. So we need to make sure that there are the same amount of things storing carbon as there are producing it. So what we could do is we could create more rainforests, okay? That would be an example of a carbon store. So producing more rainforests, planting more trees would create huge amounts of carbon sinks that can balance the carbon cycle back out. So our next piece of evidence, so that's how the carbon cycle shows us that climate change is occurring. The next way that we know there is lots of carbon is from ice cores. So ice cores are another piece of evidence used to measure climate change. So I will read this out to you. Scientists can dig out cylinders of ice to find out about temperature change. Each layer of snow each winter compresses down but contains trapped gases from the atmosphere that the snow fell through that year. Gradually those layers turn to ice. Over thousands of years these layers build up and are now meters thick. By drilling down, scientists can pull out ice cores and study the gases and chemicals from thousands of years ago. So this compressing of snow, the snow falls, within that snow you have the amount of gases that were in that atmosphere. And over time it compresses to create ice. Now obviously ice, if it's in a cold place, will last for a really, really long time. So what they end up with are these big long ice cores that show a layer of snow from each year. And they can measure the amount of carbon held in each layer of snow and can see that the more recent layers have got more carbon in than those lower down, because there was more carbon dioxide in the atmosphere when that snow fell. So what I'd like you to do is do a quick flow graph showing how an ice core is created and what it shows. So the first one is done for you. Layers of snow fall each winter that trap gases from the atmosphere. So pause your screens with this information, just a quick flowchart of how this happens. How do ice cores tell us about carbon? And do a quick heading that says ice cores above it, all right? Okay, so our first one's there, layers of snowfall each winter that trap gases from the atmosphere. Your next one could then be, gradually these layers will turn into ice. Then we could put, scientists drill up layers of these ice as your third one, and then your last one could be showing the amount of carbon held in each yearly snowfall. Okay, so a quick description of how ice cores give us evidence on climate change. Now the last thing we have got here, so we're bringing all of this together that we looked at last lesson and in today's lesson. So this bottom graph here shows temperature change over the last 420,000 years. So it shows us, this is from that point, if you remember on that first graph we did last lesson, when there started to be a massive variation in temperatures. So this shows us how temperature has changed. So we can see that there are more peaks, more highs of average temperature. This graph shows us CO2 concentrations. So the amount of CO2 measured each year. And this was taken from an ice core. So this evidence was collected within an ice core. So looking at this, there's quite an obvious link between the amounts of CO2 and the temperatures each year. Okay, so what I would like to do is, just using this information, the first thing I'd like to do is compare the CO2 levels to the temperature levels. What can you notice? So looking at these two, what is similar? Is there any difference? Can we see a link between these two things? So just a quick couple of sentences saying what the link is between temperature change and CO2. You might want to mention highs, you might want to mention lows, you might want to mention years there was high CO2 and temperature, see if there's a link. And then I would like you to read through these 5 statements, and I want you to copy out the 3 that are correct. 2 of them are not correct. I want you to copy out the 3 statements that are correct about the link between carbon and temperature. Okay, so pause your videos, a quick comparative of the 2 and then the 3 correct statements. Okay, so hopefully in your comparisons that you can see that peaks of CO2 concentration match peaks of temperature. So we can see that in the about 330,000 years ago, there was a peak CO2 concentration. And about 330,000 years ago, there was also a peak in temperature. So we can see that the pattern of temperatures and CO2 match. When there is a high of CO2, there is a high temperature, or when there's a high temperature, there's high levels of CO2, and when there is a low, they match. Okay, so of our 3 statements, our 3 that are correct. So the highest concentration of CO2 is about 275,000 years before present. That one's incorrect, because as I've just said, highest levels were about 330,000 years ago. Peaks in temperature are interglacial periods. This one is true. These are our peaks. These are when we know that we are in a period of interglacial because we've got warmer temperatures. And troughs in temperature are glacial periods. Again, this one is true because the lower temperatures are when we are in a glacial. 150,000 years ago, the CO2 was at a concentration of 280 ppmv. 150 years ago, no, it was about 200,000. So that one is also incorrect. 150,000 years ago, the temperature was about 8 degrees colder than present. So 150 years ago, our temperature was about between 8 and 6 degrees, and then now it is between 0 and 2. So yeah, about 8 degrees. So that one is true. Okay, that is the end of today's lesson. That's a bit of a short one today, but just having a look at some of the different bits of evidence that show us that there is more carbon and that carbon does link to temperature. All right, so in your books you should have the carbon cycle, carbon sink and carbon source key terms. You should have the carbon cycle sheet, a description of carbon fluxes, the carbon cycle within a tree. You should have that diagram with the questions around it, answers about the carbon cycle within a tree, how ice cores can be used as a flow chart, and the link between CO2 and temperature. Okay, so we've spent 2 lessons kind of looking at, is climate change real? What evidence do we have for it? What kind of causes are there? And we're going to come on for the rest of this unit now to have a think about the effects and what we can do to reduce it. So what are the impacts of there being more carbon? How is that? What can we do as individuals to help? All right, so we've got real interesting stuff coming up. Well done, Year 10, you are brilliant.